Good afternoon, statistics students. Here I am making yet another video for you. So I realize these are troubled times. I know some of you have emailed me about the pass-fail option. Some of you want to drop the class. I cannot tell you what to do. You have to do whatever you think is best for yourself, okay? I will not be offended if you drop the class. I will not be offended if you choose the pass-fail option. This is a very difficult situation, and I am not really an online instructor. This is my first time at Oakton doing a class completely online. When I teach, the homework is online, but I usually meet with my students for regular discussions and lectures. So this is a little bit different, and we all just have to make the best of a difficult situation, okay? With that said, let's move on and get into some statistics. And I'm looking at problem 141 in the homework titled Chapter 3 Only. So let's take a look at this. And we're going to do some problems in the 140s, okay? This video should be about, 15 minutes, maybe 20 minutes long. And we're just going to stick with problems in the 140s, okay, of your recent homework assignment. In a certain lottery, you must correctly select 6 numbers in any order out of 28 to win. You purchase 1 lottery ticket. What is the probability that you will win? So to do this, first of all, is this a combination or is this a permutation? This is going to be a combination, and the reason it's a combination and not a permutation is because of this phrase here that says in any order. In any order means the order is irrelevant, so it's a combination, it's not a permutation. Okay, so the way to do that is like this. The combination function in Mathematica is called binomial. Excuse me. The combination function in Mathematica is called binomial. Okay, so binomial, I have 28 numbers and I'm going to choose 6. So we have 376,740 different possible combinations. If I buy 1 ticket, it's going to be 1 divided by that number. Okay? So we have 1 divided by binomial 28, 6. And I want to turn that into a floating point value. So the way to do that is simply 1 divided by binomial 28, 6. Apply the n function, not little n. It's all the commands in Mathematica begin with a capital letter. Capital N, Shift Enter. This is my value. This is my value, okay? Use scientific notation. Use the multiplication symbol in the math palette as needed. Round to the nearest hundredth as needed. Okay, so the nearest hundredth means 2 decimal places. So that's going to be 2.65 times 10 to the power of -6. And so that's going to be, let's see. And Pearson agrees and says the answer is correct, okay? So hopefully that was easy for everybody. So next question. Okay. This is problem number 142. A company that has 250 employees chooses a committee of 18 to represent employee retirement issues. When the committee is formed, none of the 56 minority employees are selected. Part A, use technology to find the number of ways 18 employees can be chosen from 250. Part B, use technology to find the number of ways 18 employees can be chosen from 194 non-minorities. Part C, what is the probability that the committee contains no minorities when the committee is chosen randomly without bias? Part D, does your answer to Part C indicate that the committee selection is biased? Explain your reasoning. Okay, so Part A is pretty easy. Let's see, we have a total of 250 employees. Minority employees, yeah, it's 56. Non-minority employees is total minus minority employees. That's 194, but you know that's stated already in the problem. Okay. So the first one is, chooses a committee of 18. Committee number is equal to 18. Okay? So use technology to find the number of ways 18 employees can be chosen from 250. So binomial, total, and then we have the committee number. That is a really big number. Hold on one second. Use scientific notation. Round to 2 decimal places as needed. Use the multiplication symbol and the math palette as needed. We're going to have to do that because that number is gigantic. So that number, wait a minute. Okay, so that's going to be 1.21 times, now let's do some counting here. My God, so 1, 2, 3, 4, 5, 6, 7, 8, wait a minute, let's start over, hold on. 3, 6, 9, 12, 15, 18, 21, 24, 27. That's to the power of 27. So that's really a very large number. 10 to the power of 27. And is that correct? Okay, that is correct. Pearson accepts my answer. Okay. And part B, how many ways to choose 18 employees from 194 non-minorities? Again, we have to use scientific notation. It's a very large number. So again, that's going to be binomial. Non-minority employees. And committee number. Okay, so again, that's going to be, let's see, according to the number there, okay, 1.05 times, let's do some counting here. So that's going to be, the decimal point is between the 1 and the 0, so that's going to be, well, actually, you know what we can do? Let's make this easier for ourselves. How many digits do we have? Digits of, the percent sign refers to the last answer in Mathematica. Oh, that's not quite, That's not the command. Let's do real digits. Oh, that's not going to work either. Hold on. Let me enter this one more time. Okay. So real digits. Okay, this will make our job easier. So according to real digits, this number up here contains 26 digits. So I'm actually taking 1.05 and multiplying it by 10 to the power 25. So that'll make my counting a little bit easier. Okay, let's see what we have. Does Pearson accept the answer? Yes, Pearson accepts the answer. Okay, so let me make something very clear to you. When you're using the percent symbol in Mathematica, the percent symbol refers to the previous output. The previous output. So if I type something like 2 plus 2, okay, that's 4. If I type the percent symbol, that means 4, because 4 was my previous output, okay? Now the question is, part C, what is the probability that the committee contains no minorities when the committee is chosen randomly or without bias? All right, so we need to use the answers from parts A and B. So for part A, the answer, the number is use technology to find the number of ways 18 employees can be chosen from 250. Part B, use technology to find the number of ways 18 employees can be chosen from 194 non-minorities. Part C, what is the probability that the committee contains no minorities when the committee is chosen randomly or without bias? So we take the number from part B and divide by the number from part A. So that's going to be 1.05 times 10 to the power 25, hold on one second, divided by 1.21 times 10 to the power 27. So let me see. We can do that in Mathematica. So 1.21 times, or is it, wait a minute, yeah, 10 to the power 27. There we go. So in Mathematica, you would use times and then the caret symbol to represent scientific notation. So let's try that again. So we have 1.21, okay, 27, so times and then the caret, divided by 1.05 times and then the caret symbol 25, which means, you know, times 10 to the power 25. Oh, I have that backwards, sorry. That should be, wait a minute. Okay, let's try it again. We want the smaller number on top. So that's going to be 1.05 times 10 to the power 25 divided by, here, let me use parentheses just as a precaution, divided by 1.21 times 10 to the power 27. So that's going to be 0.0086. Okay, it's a very small probability. So the probability is do not round until the final answer, then round to 3 decimal places as needed. So that's going to be 0.009 if we round to 3 decimal places. Okay, for part D, now this probability, if we change it into a percent, is going to be 9/10 of 1%. Okay, 9/10 of 1%. That's very small. It's less than 1%. It's certainly less than 5%. So let's fill in the blanks here. Okay, the committee selection is most likely biased because the probability that was found in part C is very small. It's less than 5%. Now, let me see. Do they want an answer of yes or no? Does your answer to part C indicate that the committee selection is biased? So the answer would have to be yes. Yes, the committee selection is most likely biased because the probability that was found in part C is extremely small. In statistics, small usually means less than 5%. Okay, sometimes it means less than 1%, but in the social sciences, it usually means less than 5%. So let's see if Pearson agrees with my answer. Okay, Pearson agrees with my answer. Okay. I don't want the video to become too long because then uploading this to YouTube is going to take a long time. Let's just do a couple more problems. Okay, let's just do a couple more. Okay, this is a fun problem to do. A warehouse employs 22 workers on the first shift, 15 workers on the second shift, and 14 workers on the third shift. 8 workers are chosen at random to be interviewed about the work environment. Find the probability of choosing exactly 5 first shift workers. Okay, so again, we're going to use the binomial function to figure this out. So let's use Mathematica to help organize our data. So first shift, there are 22 workers on the first shift. Second shift, we have 15 workers on the second shift. And let's see, 14 workers on the third shift. Now, of course, nobody likes to work the third shift, right? So oops, let me put my cursor back here. So third shift is equal to 14. Let me make sure that's the right number here. 14 workers on the third shift. Okay, that is correct. 14 workers on the third shift. And let's do the total. Total is equal to the first shift plus the second shift plus the third shift. So that's equal to 51 employees. Okay. The probability of choosing exactly 5 first shift workers. Now the thing is, we have to be careful here. We're choosing 8 workers, a total of 8. We're choosing a total of 8. So the denominator is going to be binomial, total, which is 51, and we're choosing 8 workers. And that's going to be 636,763,050. And then for the numerator, we're going to have binomial, let me see, find the probability of choosing exactly 5 first shift workers. So it's going to be first shift, and we're choosing 5, multiplied by binomial second shift plus third shift, and we have to choose 3 more people, so it's the second shift plus the third shift, so that's going to be 15 plus 14 is 29, and then we're choosing 3 of those people. So the numerator is 96,224,436, and then we have the numerator divided by the denominator. Okay, so Mathematica is showing us a rational expression. We want this to be a floating point value. So to change it into a floating point value, I apply the n function, and this is how I can do it. Okay, I could also do this. I could do n and then use the square brackets, numerator divided by the denominator, and that's my answer again. So we are told here in the homework, round to 3 decimal places is needed. There are a couple ways you can do that in Mathematica. You could just do this, round my last answer to the 3rd decimal place, and usually that works. If that doesn't work, there's another way that I can show you, but maybe we'll save that for another video. So the answer is going to be 0.151, or about 15.1%. Let's check the answer. Okay, Pearson agrees with my answer, okay? Pearson doesn't always agree with my answers. Occasionally, you know, I'm a human being. I make mistakes too, just like everybody else. But Pearson usually accepts my answers, and I usually agree with Pearson's answers. Okay, let's pick one more question, and I think that's going to be the end of our video. because I don't want the video to become excessively long. Okay, this question, excuse me, question number 144 is very similar to question 143. So why don't we just skip to the next question? Sorry. Okay, question 145 is very similar. There's really no need to do that. You should be able to do that by yourselves. Question 146, you should be able to do that on your own. It's a little bit different, but it's very similar to the problem I just did. Question 147. Okay, this is a really interesting problem, and it's a little bit tricky, okay? This will be the last problem. This is going to be the last problem that I do in this video. Problem 149. Find the probability of being dealt 7 clubs and 3 cards with 1 card of each other remaining suit in 10-card poker. Now, by suit, I have to refresh my memory on this. By suit, I believe there are 4 suits in poker. We can look this up, actually, on the internet, because sometimes I get my poker terminology a little bit confused. So let's look this up. What is a suit in poker? I believe there are 4: hearts, diamonds, clubs, and spades, but you also have 2s, 3s, 4s, 5s, etc., jacks, queens, kings, and aces. I don't believe those are called suits, though. Hold on one second. Okay, it says here, in playing cards, a suit is one of the categories into which the cards of a deck are divided. Most often, each card bears one of several pips, or symbols showing to which suit it belongs. Here, let's just click on this Wikipedia article. Okay, let's click on this image. The 4 French playing card suits used primarily in the English-speaking world are diamonds, clubs, hearts, and spades. Okay, so we're not talking about 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jacks, kings, queens, and aces. We're not talking about those. We're talking about the 4 suits, which would be spades, hearts, clubs, and diamonds. So I have to make sure I get that terminology correct. Okay, let's go back to the problem. Where was that problem? Okay, so let's read the problem carefully. Find the probability of being dealt 7 clubs and 3 cards with 1 card of each other remaining suit in 10-card poker. All right, so we have to be really careful about this. So again, let's look at the Mathematica notebook. We're going to look at the Mathematica notebook. So how many clubs? Well, we have a total of 52 cards. Okay, so how many clubs do we have? We have clubs. We have 13 clubs. We have 13 spades. We have 13 hearts. And we have, oh, I did spades already. We have 13 diamonds. And total number of cards would be 52. So if I add up the number of clubs plus the number of spades, here, let me be consistent here. I'm going to call this hearts. Okay. So if I add up the number of clubs, the number of spades, the number of hearts, and the number of diamonds, I'm going to get 52, which is the total number of playing cards. Okay. So I'm playing 10-card poker here. I'm being dealt a hand of 7 clubs. Okay? So, well, first of all, the denominator, in most of these problems, you have a numerator, you have a denominator. And the probability value is always going to be between 0 and 1 inclusive. So my denominator is going to be binomial, let me spell that correctly, binomial total, which is 52, and I'm choosing 10 cards. That's a pretty big number. That's a pretty big number. So binomial total 10. Okay, that's my denominator. Now the numerators in these problems are a little harder to figure out. So binomial, now think about my choices. Okay, my choices are, I'm choosing 7 clubs. So it's going to be the number of clubs, which is 13, times binomial, the number of hearts, plus the number of diamonds, plus the number of spades, and I have 3 other cards to choose. Okay? And that's 15,682,524. So why don't I simply divide those numbers? So I have numerator divided by denominator. And again, I'm getting a rational value. I want a floating point value. I want a floating point value rather than a pure rational value. So to do that, numerator divided by denominator, apply the n function, and I'm going to get, the probability is round to 6 decimal places as needed. So what I could do is to format this number, I could choose number form, okay, oops, numerator divided by denominator. Infinity simply means give me all the digits to the left of the decimal point. And then 6, because I want my value rounded to 6 decimal places. And my answer is 0.000991. So that's a really small probability. And let me see if Pearson agrees with that. Check answer. Okay, Pearson does not agree with that. What seems to be... Hold on a second. Why doesn't Pearson agree with my answer? Hold on. Whoa. I see what's going on. Okay, so yeah, the mistake that I made here is that these 3 cards could be all hearts or all diamonds or all spades. So my numerator is not correct. This part of the numerator is not, this is not correct. So my numerator is off. Let's do this. Let's do the numerator again. The numerator is equal to binomial. I have 7 clubs times binomial. I'm supposed to have 1 heart times binomial. I'm supposed to have 1 diamond, and then binomial, I'm supposed to have 1 spade. So that number should be, okay, that's a different number, so let's try this again. Number form, numerator divided by denominator, make it a floating point value instead of a rational expression, infinity, and I want my answer rounded to 6 decimal places. Oh, no wonder I didn't spell this command correctly. In Mathematica, spelling is very, 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 very important, okay? Okay, so this time we have a somewhat smaller probability, although the magnitude is about the same. So 0.000238. 238. Now let's see if this is correct. Yes, that is correct. Okay, Pearson likes my answer. Okay, guys, I think that's going to be enough for now. If you have questions, if you want to learn more about Mathematica or using Mathematica to solve statistics problems, you need to email me. Do you have to use Mathematica? No, you can use your calculator, you can use Microsoft Excel, you can use whatever tool you know how to use, although I recommend that you acquire some familiarity with Mathematica because it is a very powerful computational tool that you can use for probability, statistics, calculus, algebra, physics, chemistry, engineering, geometry, all kinds of technical areas and disciplines. I strongly recommend it. It is really good software. Okay, it's very, very good software. Okay, I think that's going to be it for now. I hope everyone has a great day, and I hope you're staying safe and healthy. And goodbye for now.